deep thank you to the organizers of this, this conference. It's a great pleasure to be here and to give you a talk about paternal aging and the origins of spontaneous mutations. And I thought a good place to start such a talk would be with Ramjit Raghav. So Ramjit is the, claimed to be anyway, the oldest father in the world. He had this child he's holding at the age of 96 and said he wanted even more children. Sadly, that was not to be. He passed away earlier this year. But his image serves to remind us that male and female reproduction are very different in the sense that men don't suffer the same precipitous decline of fertility in midlife that women do. Men can still sire children into their dotage, but what changes with time is the incidence of diseases in their offspring. And we have known about this for some time. The classic conditions are things like Apert syndrome and achondroplasia, which increase exponentially with the age of the father at the moment of conception. These particular conditions, I think, represent very particular cases. They are mutations in fibroblast growth factor receptors 2 and 3, and the etiology involves something called the selfish spermatogonia selection model, which means that when germ cells acquire these particular mutations, they undergo a very rapid clonal expansion. So that if you take a test section through a testis of a 78-year-old male, you'll find sudden clusters of these germ cells in his seminiferous tubule. But I think this is a very particular case. That's not how most mutations arise in the male germline. We have, as I've said, known about these conditions and their relationship with these mutations for decades. More recently, we've become aware that a whole range of other diseases, and these are largely brain disorders such as bipolar disease, autism, spontaneous schizophrenia, attention deficit to hyperactivity disorder, epilepsy, all of these conditions show a strong correlation with the age of the father at the moment of conception. And the obvious question is, well, why would this be? Well, one thing that happens as fathers age is that the mutational load carried by their children increases as a linear function of their age. And this is data actually on the Icelandic population, and it shows this very beautifully, that as fathers age, there's a linear increase in the incidence of mutations in their children. Two things to note about this particular graph. First is, look at the x-axis. These are not old men. These are men who are between the ages of 15 and 45. They're men of normal reproductive age. And the number of de novo mutations increases, and then it gets to a certain point when the dots turn from black into red, as the incidence of autism suddenly starts to increase. So there is something happening in the male germline with age that leads to an increase in mutational load in the children, and that mutational load then correlates with these various disorders in the offspring. So what is that something? What is going on here? Well, the classic explanation is replication error. So if you're a 15-year-old boy, your germ cells have been through 35 rounds of replication. But if you're a 50-year-old man, your germ cells have been through 840 rounds of replication. And with every round of replication, there's a risk that a defect will occur, an error will occur, that will generate a mutation. And that's been an explanation that the field has been, I guess, happy with for a long period of time. But it's certainly not the whole story. And we know that because if you look at the incidence of paternal and paternal-derived mutations in children as a function of parental age, there is a difference between paternal and maternal, even at the age of 15 when this cohort are first having their children. So it can't be replication error at this early age. There must be something else going on which is causing these mutations. And incidentally, if you look at these graphs, what it tells you is that ultimately 75% of de novo mutations will originate in men, not in women. So something happening in the male germline responsible for these mutations. We've known for a very long period of time that human semen quality is poor. You only have to look at this micrograph to see that there are very few normal looking cells in an average human ejaculate. And if you look at their motility, this is actually quite good motility, but these cells are moving around at about 25 microns a second. If we were looking at the sperm cells from the wallabies that are hopping around the bush around me, their sperm cells are moving around at 300 microns a second, so 10 times faster. So human spermatozoa, not particularly good, and as a consequence of that, roughly 1 in 20 males has a fertility problem. And mostly this is due to defective sperm function. Most men produce enough spermatozoa to fertilize an egg. You don't need very many. But in cases of male infertility, the sperm have lost their capacity to either find or fertilize the egg in vivo. Many years ago, more years ago than I care to remember, we used bioassays to look at the fertilizing capacity of human sperm. And this is that bioassay is the zona-free hamster egg penetration test, as it was known, a much maligned method of detecting the fertilizing capacity of human sperm. It was never meant as a diagnostic technique, but as an experimental technique, it was actually quite valuable. And it's enabled us to look at the capacity of cells to undergo a series of changes. Sperm cells, human sperm cells, will only fuse with a hamster egg if they have capacitated, acrosome reacted, and generated a fusogenic equatorial segment. So the biology of this system was reflective of the homologous situation. And although it was never a good diagnostic assay, it was a very good experimental technique and enabled us to generate this correlation, which basically summarizes a decade of work. And that is that if you look at the patient population, you will find that most, certainly not all, but most men who had sperm that performed very poorly in this assay exhibited high levels of reactive oxygen species generation. Whereas you look in the fertile controls, the story is essentially the opposite, where you have high rates of sperm oocyte fusion, low levels of reactive oxygen species generation. This has been a very large field now. If you put reactive oxygen species and sperm into PubMed, you'll come up with thousands of references. And we've learned a lot about how these factors intersect. The thing I want to highlight today is that in these subfertile men, the reactive oxygen species that are being generated are targeting the DNA in the sperm nucleus and the mitochondria. The guanine residues are particularly vulnerable to oxidative attack, and when that happens, you generate this base adduct, 8-hydroxy-2'-deoxyguanosine, or 8-oxo-G for short, and this destabilizes the DNA backbone, leading to A-basic sites and DNA fragmentation. Indeed, if you look at the level of oxidative DNA damage in human sperm, it correlates very well with the levels of DNA fragmentation, leading us to conclude that most, certainly not all, but most DNA fragmentation in human spermatozoa is oxidatively induced. So DNA fragmentation is definitely a characteristic of human spermatozoa. We have known this for a very long period of time. Using COMET assays to look at DNA damage, for example, you can show that in the patient population, a large number of men have much higher than normal levels of DNA fragmentation in their sperm. And this is highly correlated with the age of the donor. So if you're over the age of 36, then you have 3 times the amount of DNA damage in your sperm compared with somebody under that age. And the relationship is approximately linear. The older the donor, the more DNA damage you will find. These data were generated using a COMET assay. More recently, Don Evanson has pulled together a lifetime's work, over 25,000 men analyzed for DNA fragmentation using the SCARSA assay, and he's just published the results in fertility and sterility. And this shows the smoothed percent DFI as a function of age. So very clear here that the older the men, the more DNA fragmentation they have in their gametes, and this DNA fragmentation is oxidatively induced. Well, if oxidative DNA damage is so important to the cells, how do they actually protect themselves from this kind of damage? This is a very simplistic presentation of the base excision repair pathway. This is meant to portray a DNA duplex. This little red box is the oxidized base, and it's the enzyme that initiates DNA repair is called OG1. It's a glycosylase, and it serves to remove this oxidized base from the DNA, creating an A-basic site. Sperm do have OG1. They have it in their nucleus, they have it in their mitochondria. There are two isoforms, one for the nuclear DNA, one for the mitochondrial DNA. And we can confirm the presence of this enzyme, both biochemically and by proteomics. So tick, these cells definitely have OG1. The next enzymes or proteins involved in base excision repair are the AP endonuclease and a scaffolding protein called XRCC1. Sperm cells do not have either of these proteins. They don't have AP1, they don't have XRCC1. Doesn't matter if you look by immunocytochemistry or Western blot, they're simply not there. And because sperm do not have these proteins, the base excision repair pathway stalls. So all a sperm cell can do is remove the oxidized base and create an A-basic site. And that's all it can do. But we shouldn't fret, because the egg is actually replete with AP1 and XRCC1. So in a perfect world, I think what's supposed to happen is that if DNA becomes oxidatively damaged in the sperm cell, it will remove the oxidized base to create an A-basic site, and then we'll leave it to the egg to complete the DNA repair pathway. So it's a beautiful example of male-female collaboration or collusion, if you like, in order to solve the problem of oxidative DNA damage. There is, however, a problem, and that problem is that the oocyte has very little OG1. By immunocytochemistry, by Western blot, very little of this enzyme. So if a sperm cell should fertilize an egg still carrying these oxidized base residues, there's nothing that the egg can do about it, because it has very little capacity to remove that. And these adoxo lesions will persist into S phase of the first mitotic division and cause a mutation. And this is a real risk, because we know that if we look at the average human ejaculate, you can find many cells that are still adoxoguanine positive. And those cells, once they fertilize the egg, will be a challenge. And if those oxidized residues persist into the DNA replication, it may well create mutations. The way it does that is through something very interesting called Hoogstein base pairing. Now, I don't suppose there's much interest in biochemistry out there, but just everyone will know that guanine pairs with cytosine and adenine pairs with thymine. However, if the guanine residues become oxidized, they develop a new capacity which, by reorientating themselves, enables them to bind not to cytosine but to adenine. So you get these adenine adoxo-G base pairs, and in the next round of replication, that oxidized base will be replaced by a thymine. So you get a GC to TA transversion. And if you actually do the experiment, you take a mouse and you knock out all of the DNA base excision repair enzymes, and produce mice that have very high levels of 8-oxoguanine in their gametes, their offspring have very miserable lives. They live a very short time compared to the heterozygotes. They accumulate a lot of cancers, and they have mutation rates that are 18-fold higher than basal level, mostly GC to TA transversions, as we would have predicted. In humankind, I think you see this kind of thing in, for example, smoking. So if you're a man and you smoke heavily, there is a lot of DNA damage in your gametes, and it's mostly oxidative DNA damage. And we can't do the experiment in humans, but if we do the experiment in mice and expose them not to cigarette smoke, but to benzpyrene, the major mutagen in cigarette smoke, then the young are born carrying high levels of mutations, and they're mostly the GC to TA transversions and GC to AT transitions that we would have anticipated. This kind of oxidative DNA damage to human spermatozoa in the case of men who smoke heavily doesn't have a massive impact on their fertility. However, it does have an impact on their offspring because of the mutations it generates. And this is just the result of a meta-analysis published by Lee, and there are other more recent meta-analyses confirming this and showing that the children of men who smoke have a significantly elevated chance of developing childhood cancer. And this, for me, is a game changer as far as smoking is concerned. If I say smoking, you normally would think of diseases of the perpetrator. You'd think of coronary heart disease or lung cancer. But what's much more sinister is that if you smoke heavily, you induce high levels of mutation in your gametes, and that's responsible for increased childhood cancer in your offspring. And because the mutations are in the germline, there is the potential that this will persist with your lineage for a significant period of time. Smoking has been responsible for introducing millions of mutations into our species, the consequence of which we still don't really understand. So, if we summarize all of that, what I think is happening is that the things that we've been talking about, paternal age and smoking, but there are many other things as well, serve to create a state of oxidative stress in the germline, which leads to oxidative DNA damage. These sperm then fertilize the egg, either naturally or they're induced to do so with IVF or ICSI. And then the poor egg has got just a few hours to try to repair all that DNA damage before we initiate DNA synthesis for the first mitotic division. And if the egg makes a mistake at that point, it will create mutations that then are responsible for the various brain disorders and cancers that we see in the offspring. And this is particularly the case with 8-oxoguanine residues that the egg is very defective at repairing. So if all this is true, then it becomes very interesting to know whether there are hotspots for oxidative damage within the sperm genome. Now, the way that DNA is packaged into a sperm head is really fascinating. The sperm becomes complex with protamines and develops these kind of donut-like structures known as toroids. Within these toroids, the condensed state of the DNA is such that it's almost crystalline, and it's actually very difficult to damage that DNA. But each of these donut-like toroids is connected to the next by a piece of interlinker DNA, which is attached to the nuclear matrix. And it turns out that this is the DNA which is vulnerable to oxidative attack. And if we look at sperm cells and consider which areas of the genome become oxidatively attacked, we find, as we might have predicted, that the damage is spread across the genome. And generally speaking, the bigger the chromosome, the more oxidative damage there is within it. But there are two exceptions, really interesting exceptions. One are the sex chromosomes. So the sex chromosomes are somehow protected from oxidative attack. My colleague Joel Dreve has done exactly the same study in mice and finds exactly the same thing. But there is one chromosome, chromosome 15, which is particularly vulnerable to oxidative attack. And we don't yet know why. It could be its position in the sperm head, but it is particularly vulnerable. This is chromosome 15. And down here, I've aligned the oxidized base lesions we find across that chromosome. So we find these oxidized bases everywhere, but there is a domain here around 15q11 to 15q14-15, where we see a highly elevated level of oxidative DNA damage. Interestingly, to that region of the genome has been traced mutations that cause autism, bipolar disease, schizophrenia, and Marfan syndrome. And interestingly, all of these conditions are highly correlated with the age of the father at the moment of conception. So what we think happens is that as men age, they develop more and more oxidized DNA damage in their spermatozoa. This oxidative DNA damage is concentrated in this area of the genome on chromosome 15 and induces mutations, different kinds of mutations, duplications, deletions, and so on. But these mutations are then responsible for the appearance of these conditions in their offspring. And of course, age is just one way that you induce oxidative stress in the germline. There are many others, and we've considered one, which is smoking. And as I've already told you, as men smoke, and it doesn't matter if you smoke before conception or during pregnancy, there is an increase in the risk of childhood cancer in your offspring. This is the mean risk, and these are the confidence limits. But there is an increase in the risk of cancer in your offspring. And then if you look at where the mutations are that cause this disease, you find that they are exactly in that spot where the oxidative damage is occurring on chromosome 15. And of course, infertility is another way in which you induce oxidative stress in the germline. So it would be entirely predictable that conditions like autism would be increased in the children of patients who are coming for assisted reproductive technology. And indeed, this study by Kissin et al. And quite a large number of patients from California, over 30,000, did show an increase in the incidence of autism in children conceived by ICSI, not IVF. And we presume this is because with ICSI, there is less sperm selection than there is with IVF. At least with IVF, you've got the zona pellucida to help you, and motility to some extent, to help you select the best gametes. But you don't have that luxury with ICSI. And so DNA damaged sperm are being inserted into the egg, and one of the consequences you see is this increased risk of autism. It's a small increase in risk. It represents about a 1% increase in risk. And at a patient-for-patient level, that risk may not be considered significant. But when, as in Australia, you've got 5% of your population being produced by IVF, this starts to have consequences at a national level, many more cases of autism because of the widespread practice of ART in our general population. Now, what can we do about it? Well, there are just two things we can do currently. And one is to try to isolate sperm cells that are free of oxidized DNA damage before we use them for ART. There are a number of different techniques which people use routinely in their clinics: density gradient centrifugation, swim-ups, some people do a swim-down, glass wheel filtration. Suddenly, a lot of microfluidic systems have appeared on the market, and employing principles like chemotaxis, rheotaxis, and thermotaxis to help isolate the cells. And in my own laboratory, we've been trying to develop an electrophoretic technique to isolate sperm cells. And this is just data from that electrophoretic technique showing that sperm cells from a variety of different sources, when they're isolated using electrophoresis, so the idea here is have much higher than normal levels of negative charge, they have lower levels of DNA damage. I don't advocate for any particular method. I'm just saying that we need to very carefully compare these methods when thinking of the best way to isolate cells for IVF. And then finally, antioxidant therapy. For this purpose, we use the GPX knockout mice produced by Joel Dreve. This is an ideal mouse because it has a very oxidative stress localized to the epididymis. The testis is absolutely normal, but in the epididymis there is no antioxidant protection, and the result is the sperm accumulate large amounts of oxidized DNA damage. If you give these mice antioxidant therapy, then you both increase sperm number and decrease the amounts of DNA damage. So, in summary, oxidative stress is a major contributor to male and female infertility. It's a major factor in the etiology of DNA damage. It's exacerbated by factors like age, smoking, and other things I haven't mentioned, like obesity and chemical exposures. It increases the mutational load in the offspring, particularly on chromosome 15, and that may be correlated with conditions such as autism and childhood cancer. And to resolve this problem, we need to use improved methods of sperm selection and think about clinical trials for antioxidant therapy.